Welcome to our lecture on gas laws, and as you can see, we're getting classy with this one. So what do the gas laws do? Well, they really describe how gases behave when they're subjected to changes in pressure and changes in temperature. We can also expand this and talk about kinetic theory, the energetics of a system of gas molecules or individual molecules of the gas. But first, we have to think about how does gas actually behave? So if we have gas in a container and we add more, essentially inflating something like a balloon, we take something like a balloon and we blow into it, we're adding oxygen and nitrogen, we're adding gas molecules. So if we inflate a balloon, we add gas molecules. Now, if we double the number of gas particles, we'll double the pressure in a vessel. That's if we keep the volume and temperature constant. So in order to really quantify a gas, we need to measure 4 variables of the environment: the pressure, the temperature, the volume, and the number of particles. How much stuff have you got? And so the pressure and number of molecules are directly related. More molecules, more collisions occur. Fewer molecules, fewer collisions occur. Not only does this affect the pressure, but also the energetics of the particles within. So let's take a look at a simple case. Here we have a bike pump, and this is hooked up to this cylinder which has a pressure gauge on it. This is at 1 atmosphere. This is the initial pressure, PI. So this is essentially atmospheric pressure. If we double the number of molecules by pushing down the plunger on the pump and pushing air into the cylinder, then we will double the pressure. So now we're at 2 atmospheres. If we remove molecules from the container, here we've pulled out the cork, then the air will flow outwards and you will end up with a reduction in pressure inside the container. The pressure will continue to decrease until it equalizes, reaches an equilibrium with the environment around it. So the pressure inside this vessel will continue to decrease until it reaches the outside pressure. So it will stabilize back at 1 atmosphere, the atmospheric pressure of the environment around it. So molecules will naturally move from a high pressure gradient down to a low pressure gradient. They will move from high to low. You can move from low to high, but then you'll have to put in work. You'll have to use a pump to push the molecules the opposite way. But under nature, they will go from high to low pressure. So what about volume? We've talked about pressure there. What about volume? Well, if we change the container size, change the volume of the vessel, then the molecules have less space to move around. They'll hit the sides of the container more often and interact more often with one another. So as volume decreases, pressure increases. So in a case like this, we can again take a cylinder here, shown by this yellow line, and put a piston into it. We can hold this at 1 atmosphere, so the pressure of the atmosphere around it, normal atmospheric pressure. In here we have a volume of 4 liters. Now, if we move the piston downwards, we still have the same amount of gas molecules. They're now compressed into a much smaller volume. So now we're looking at a pressure increase of 2 atmospheres. So if we halve the volume, we'll double the pressure. So the pressure on this gas increases as the volume decreases. So the pressure and the volume are inversely related to one another. As pressure increases, volume decreases. When we consider the temperature of a gas, if we raise the temperature of a gas, we will increase its pressure. This is only if the volume of the vessel it's contained in is held constant. So with every gas law problem, you should check to see which variable is being held constant and which one is changing. The variable that's changing, in this case temperature, will have a dependence on pressure and vice versa, and you should expect to see that variable alter as well. Additionally, when we raise the temperature of the gas, the molecules will move around much more quickly as they will have more energy per molecule. This will cause them to hit the container walls and one another much more vigorously, much harder, and translate more energy. The only way to increase the temperature of the system when held at a constant pressure is to increase the volume. And I ask you to think about that and read about that in the book just a little more. So if we take our pressure vessel again, here's our piston and here's our cylinder. And in this case, we have 1 liter of gas held at 1 atmosphere at a temperature of 300 K. The temperature is then increased to 600 Kelvin. One of two things will happen in this case. One of them, since we've doubled the temperature, is that the volume could increase to 2 liters and hold at 1 atmosphere. Or we could keep the volume constant and increase the pressure within the vessel to 2 atmospheres. So there's one of two things could occur, and you should always make sure to see which variable is being held constant in each case when endeavoring to solve a problem. So when we're dealing with the gas laws, we assume gases behave ideally. What do we mean by that? Well, we assume particles have no volume and we don't worry about attractive forces between the molecules, electrostatic and such. That makes our calculations a little bit easier. Otherwise, we'd be there for a very, very long time solving a relatively small problem. It also means that, this approximation isn't too bad. It actually works quite well until you start getting onto very microscopic scales. So if you're dealing with enormous tanks of propane, for instance, there's no real need to worry about getting down to that level where the electrostatic attraction between the molecules will matter. So these approximations work well. So how do particles in an ideal gas behave? They undergo only elastic collisions. So that means that they're not really exchanging energy between one another. They enter a collision and they go out of that collision with the same energy they entered. Maybe a different direction, but they don't change their energy. They move in constant, random, or straight line motions. They do not attract or repel each other. And the final point, when we talk about kinetics, they have an average kinetic energy, that's Ke here, that directly relates to the temperature in Kelvin, which is something we've already discussed when we looked at the Kelvin scale. So, let's talk about the laws. And this is going to seem like there's a lot, but these will all simplify down into one single law, so bear with me. First of all, there's Boyle's law. And this says at constant temperature and pressure, pressure and volume are inversely related. As one goes up, the other will go down. So PV, pressure times volume, is some sort of constant. So it's easier to use P1V1 equals P2V2. And this was the work that Boyle did with his very fine wig here to prevent him from getting lice. And you can see at constant mass and temperature, P1V1 equals P2V2. Bear with me, there's a simpler version of all of this coming. So Boyle came up with his constant, PV equals K. There's then Charles's law. Volume of a gas is directly proportional to the temperature in Kelvin if the pressure is held constant. Or V is equal to KT, where K is a constant. So he said V over T was equal to K, or V1 over T1 equals V2 over T2. So he said the volume and absolute temperature of a gas are directly related at constant mass and pressure. or V and T, nice straight line relationship, V over T will give you K. Thank you, Charles, a slightly scruffier scientist in this particular case. And finally, there's Gay-Lussac's law. Definitely a Frenchman in this particular case, as you'll see from the next picture. The temperature and pressure of a gas are directly related at constant volume. So P equals kT, where K is some constant. So P over T equals K, or P1 over T1 equals P2 over T2. So again, a nice straight line. There's Gay-Lussac with his nice little spectacles on. P over T is equal to K. Now, there's no need to remember all three of these laws, because they all came up with a handy little constant, and when you put them all together, you end up with what's called the combined gas law. And this is for a situation where only the number of molecules stays constant. And you can see this is the final form of all three of those laws put together. All three of these people were working independently, and when they put their work together, they realized it made one big gas law. And P1 V1 over T1 is equal to P2 V2 over T2. The task is to find one of these values when two of the others are changing. So here we have a situation, the combined gas law, and it contains all the other gas laws. So if the temperature remains constant, temperature is eliminated from this equation, and you end up with P1 V1 equals P2 V2. And that's Boyle's law. Again, if the pressure remains constant, pressure is eliminated in this equation, and you get V1 over T1 equals V2 over T2, which is Charles's law. And again, with Gay-Lussac's law, if we hold the volume constant, we'll end up with P1 over T1 equals P2 over T2. So remember the combined gas law. So in Boyle's, Charles, and Gay-Lussac's law, two variables were allowed to change. This is our version, the combined gas law. Please remember, when you're using this gas law, make sure that all your temperatures are in Kelvin. Even if the question gives them in Celsius or Fahrenheit, when you use the gas law, convert everything to Kelvin. There's an alternate form if you think about how these are divided out, where you could cross multiply these and you could have P1 V1 T2 equals P2 V2 T1. You can see this written in some places. I tend to use this version and then substitute as needed and rearrange as needed. So if we're going to characterize our gas, it'll occupy some volume V, exert some pressure, pressure equals force over area. It'll have a quantity of material, little n, or as we'll see later, big N, and a temperature of T. Remember, if you're looking at a graph, a small t usually denotes time, a capital usually denotes, in this kind of physics anyway, temperature. So when using your gas laws, I cannot stress enough, make sure your temperature is in Kelvin. Make sure your pressure is in pascals. And there's lots of different units in pressure. If you're an engineer, you probably use PSI. If you are an atmospheric physicist, you probably use atmospheres or bars. The Pascal is one of those annoying units, which is extremely big. So you always wind up with relatively small numbers in these cases. So 10 to the negative 5 bar, 1 Pascal, 9.87 times 10 to the minus 6 atmospheres, or 1.75 times 10 to the minus 4 psi. You may also see other units for pressure, such as torr, or millimeters of mercury. These are things used in meteorology and things like that. I will not give you those, but if you see them, those are one of those things where you should just look up a conversion factor and just apply it to get everything in pascals for your calculation. So let's take a look at a calculation. So pure helium gas is placed into a tank with a movable piston. It has an initial volume of 15 times 10 to the minus 3 cubic meters, an initial pressure of 200 kilo. So this is 200 times 10 to the 3 pascals, and an initial temperature of 300 Kelvin. The volume is decreased, so this plunger is pushed down to 12 times 10 to the minus 3 cubic meters. This increases the pressure to 350 kilopascals. Find the final temperature of the gas and assume that helium is an ideal gas. If this is not stated, then state it yourself. I will always assume an ideal gas is being used in our problems. So here are our variables. This is how you should do each and every problem. Write out the variables, especially with the gas law. See what you've got, compare the values, and see how they are changing. So find TF. We have VI, PI, TI, VF, PF. We want to find TF, the final temperature of the system. So pull up our combined gas law. PI VI over TI is PF VF over TF. We want TF. Rearrange for TF. Make sure you're comfortable rearranging this formula to find any one of these variables, PI, VI, TI, PF, VF, or TF. Usually it's a good idea to practice that to make sure you're confident in the rearrangement that you've done. This isn't particularly complicated, but if you're faced with something like this on an exam, then quick rearrangement is something that tends to worry people. So make sure you're confident with being able to find any one of these variables given these values or other values. So here's our rearrangement. TF equals PF times VF over PI VI times TI. Now we can substitute in. I haven't changed the kilopascals here since these units will cancel anyway, but you could have put times 10 to the 3 on both of these. I have converted our volumes here, so I left them as they were in 10 to the negative 3. So multiply, this is our volume, this is our pressure, volume and pressure again, and multiplied by 300K will give you 420 Kelvin. Not a terrible problem, just make sure your rearrangement is correct and your substitution is correct and in the right units. Always look at your final answer as well. Here we had an initial temperature of 300 Kelvin. It's quite reasonable that we'll end up with a 420 Kelvin temperature at the end. So, you know, about 120 Kelvin increase. If this was 120,000 Kelvin or something, you might want to look back and make sure that your decimal places are all correct. The other thing to be careful of is making sure you understand how to convert volumes. So volumes are often a bit tricky in terms of the way that the numbers change when you substitute them into the formula. Commonly used units are such things as the milliliter. That converts to a cubic centimeter, or again to a cubic meter. So make sure you're familiar with how to convert between volumes or what kind of numbers you should expect to see for a converted volume. So 1 milliliter, 1 times 10 to the minus 3 liters, turns into 1 cubic centimeter, or cc. 1 liter turns into 1,000 cubic centimeters. 1,000 liters, therefore, is 1 cubic meter. So make sure you're okay with these. If we look at the same with masses here, 1,000 milligrams is 1 gram, 1,000 grams is a kilogram, 1,000 kilograms actually equals 1 metric ton. So these slides are really here for your information. So 1 cc is 1 cubic centimeter, 1 milliliter, 1 cubic centimeter there. 1 liter, 1,000 milliliters, 1 kiloliter, 1,000 liters, and you see where this goes. I'm not really going to deal with cubic inches. If you're dealing with engines and displacements, you may see this. I'll also not go into quarts. I will leave things in liters or cubic meters for you to convert to. Same with cubic feet. So remember, when you are converting between volumes, when you're looking at a milliliter, this essentially is a centimeter sided cube, 1 by 1 by 1. So 1 liter here is a 10 by 10 by 10 centimeter cube. So you will frequently have to convert between volumes, quite often between cubic centimeters and cubic meters, especially if you remember the conversion to liters. So 1 cubic centimeter is 1/100th of 1 cubic meter. So make sure you're preserving decimal places and take a look through the book about how this is done to make sure you understand what you're reading and how you're converting these. So some of the values can actually turn out to be quite surprising at first glance. So let's take 85 cubic centimeters and convert it to cubic meters. What we're actually doing is saying this is 85 cubic centimeters and we're multiplying it by 1 over 100 cubic centimeters. So 1 over 100 cubed. That translates to 85 over 100 cubed. This means your volume is going to decrease in terms of its number, and you'll end up with 8.5 times 10 to the minus 5 meters. I've also given this in terms of zeros, so 0.000085 meters. I would prefer this as standard notation. Doing the same again, let's now convert 0.085 cubic meters to cubic centimeters, so going back the other way. So here's 0.085 cubic centimeters times 100 over 1 meter. This will give us 0.085 times 100 cubed, which will give us 85 times 10 to the 3, or 85,000 cubic centimeters. So let's take a look at a problem. Here we have a sealed bottle of air at an initial pressure of 101 kilopascals and a volume of 30 cubic centimeters with an initial temperature of 27 Celsius. For some reason, someone throws this bottle into a fire and it's heated to 200 Celsius. What's the new pressure inside the bottle? So the first question you should always ask yourself with a combined gas law problem is what's held constant. And I'm telling you, in this problem, we're assuming the bottle volume does not change. So V is held constant. So VI equals VF. So again, writing our variables is useful. Our initial pressure, initial volume is final volume, which is 30 cubic centimeters. Initial temperature, final temperature. What's the new pressure inside the bottle? Same question. So I make the statement and put it in a box so you can see it clearly that VI equals VF. And that's a good thing to do when you're going through problems, is to remind yourself what's constant. State the gas law in its entirety. PI VI over TI is PF VF over TF. If VI equals VF, we can get rid of our volume and we'll end up with the simplified relationship of PI over TI equals PF over VF. We now want to find out what the new pressure is. So what is the final pressure? Rearrange. So TF over TI times PI, and now substitute. We can leave everything. In this case, we can leave it in kilopascals and quote kilopascals at the end. So here we've got 473 Kelvin with 300 Kelvin times 101 kilopascals equals 159 kPa, or 159 times 10 to the 3 pascals. So that's how you'd use the gas laws, and a bit of a cautionary note on how to use volume. As well as the gas laws, there is the ideal gas law. And this gas law talks about the actual energetics of the system. And this relates pressure and volume to how much material you have, N in moles, how many moles of a material, how many moles of a gas you have, R, a universal gas constant, and temperature. So really it's relating pressure and volume to temperature once again. But the ideal gas law is extremely useful when we start to talk about the energetics of a gas. This R is a universal gas constant and is given as 0.0821 liters times atmospheres over mole Kelvin, or energetically 8.315 joule per mole Kelvin. This is usually the version I will provide, but depending on what pressure value is used, you can often see different versions of this constant in different websites and books. So if you are looking at other sources when you're looking to study and looking through the class, be careful as to what value of R you are using. So the ideal gas law uses N, which is the number of moles of a gas that we have. And that really means we have to invoke Avogadro's hypothesis to figure out how much mass of our gas we have. The volume is proportional to the number of molecules at some constant temperature and pressure. So V, the volume, is proportional to how many moles of the material you have. So V, the volume, is equal to K, some constant, times N. And we've really put this into the gas law here, the PV over T times N here equals P2V2 over N times T, which gives us a constant which we call R. And as I said, that ideal gas constant, depending on what your pressure value is, depends on what the value of the constant is. So in the ideal gas law, R is a constant for all gases, and you need it for your calculations. And this was experimentally derived for lots of gases at extremely low pressures. So the ideal gas constant, here we are, we've seen a couple of these before. Here's one quoted, 0.0821 litre atmospheres per mole Kelvin. And as I said, if you change the pressure and give it in millimeters of mercury here as a meteorological kind of pressure, then you end up with a value of 62.4. That means you'd have serious problems using it in the kind of equations we're looking at. We tend to use this version. 8.31 liters per kilopascal times Kelvin moles. And that's 8.31 joules per Kelvin mole. And this joule, this energy unit that's inserted in here, is extremely useful when we talk about the energetics of the gas. So let's just talk about how we deal with that N in there. And this might be a reminder to those of you who've done basic chemistry. So the molar mass of a gas can be determined by the density of your gas. Density is usually in physics given as rho, the Greek letter, like a little p here, little stylized p. And this is mass per unit volume, or m over v. The molar mass is the mass divided by the number of moles of material you have, m over n. N, how much material we've got in moles, is also PV over RT. And remember, when we're characterizing our gas, N is measured in moles, and 1 mole is 6.02 times 10 to the 23 objects. So in our case, 1 mole of material would be 6 times 10 to the 23 molecules of that material. But how does that relate to the mass of the material? Well, 1 mole of carbon atoms has a mass of 12 grams. Atomic number here. If you go to your periodic table, carbon has a value of 12. 1 mole of oxygen atoms has a mass of 16, again from the periodic table. So usually you'll have the mass of a substance and then convert it to the number of moles. And the number of moles is the mass over the molecular mass. So that's what we were doing here. The molecular mass of carbon is 12, the molecular mass of oxygen is 16. So when we talk about moles, we're really talking about this magical number of 6.022 times 10 to the 23, not the 1950s movie, The Mole People, which is, by all accounts, awful, but extremely funny. So when we talk about the mole, this is our basic unit of measurement that converts from atomic mass to grams. Carbon-12 is used as the standard. So in 1 mole, we have a number of atoms of C12 in 12 grams of C12. So there are 6.022 times 10 to the 23 carbon atoms in 12 grams of carbon-12. That's what I mean by C12, standard isotope of carbon, or non-isotope of carbon in this case. So 6.022 times 10 to the 23 of anything is considered to be a mole. And that's what we mean by Avogadro's number that we multiply by. So what's going to become important later, especially when we show you a slightly different version of the ideal gas law, is converting between the number of moles, little n, and the total number of particles in the system, which is big N. So don't take your n's for granted. Make sure you're paying attention as to whether you're seeing a big N, which is how many particles you have, versus a small n, which is how many moles of a particle you have. So to find the total number of molecules, big N, in a sample of material, we have to take our Avogadro's number, which is our 6.022 times 10 to the 23, and multiply it by the number of moles. And that means looking at the atomic mass on the periodic table. The atomic mass of carbon is 12, atomic number of 6. That means it has 6 protons, 6 neutrons in carbon-12. Protons and neutrons have a tiny little mass. We set this mass equal to the atomic mass unit, so carbon-12 has a mass of 12. So the atomic mass on the periodic table is really a weighted average of masses of all isotopes of an element. But it's actually more useful to associate the atomic mass to a mass in grams or kilograms. For our purposes, we will always use kilograms. So, a little bit of repetition. As we said, the mass of 1 mole of something is its molar mass. 1 atom of C12 is 12 atomic mass units, and 1 mole of C12 is 12 grams. So the atomic masses convert directly from atomic mass units and atoms to mass per mole. For any element, we can talk about the molar mass. The molar mass is equal to the atomic mass from the periodic table, but we like to use grams per mole rather than the atomic mass unit. So the atomic mass of lithium is equal to 6.94 atomic mass units. So 1 mole of lithium is actually equal to 6.94 grams. That is a molar mass of 0.00694 grams per mole. And you can look up the molar mass of any of the elements. So for something like sulfur, we're looking at 32.06 grams per mole. Silver, Ag, is 107.9 grams per mole. Now, we have to be a little careful when we talk about a compound. And what do we mean as a compound? Well, for a compound, we mean something like carbon dioxide, CO2. We have 1 carbon and 2 oxygen atoms to account for. In those cases, to find the molar mass, we have to sum the molar mass of each element and multiply by the number of atoms of that element that are present in the compound, which is a lot simpler than it sounds in words. So for CO2, we have 1 carbon, so this is carbon dioxide gas. We have 1 carbon, C times 1 is 12.01 times 1 gives you 12.01. For oxygen, we have 2 of those, that's 16 times 2, that's 32. So rounding a little, that gives you about 44 grams per mole. So if we determine the mass in grams of the following elements, 2 moles of Au, of gold, we'll say 2 moles times, from the periodic table, 196.9 grams per mole will give us 3.9 times 10 to the 2 grams. Zinc, 4.37 moles. Multiply that by 65.4 grams per mole. Again, go to your periodic table. That'll give you 2.85 times 10 to the 2 grams. Likewise, we can determine a number of moles. Here we have copper. It's 1.254 grams. Multiply that by 63.5. We'll end up with our 4 moles. And finally, sodium, 2.12. Multiply that by moles per gram, 23. We'll end up with 0.52 moles of sodium. So how many moles do we have in 18 grams of water? 1. Find the molecular weight of water. Hydrogen, 1 gram per mole. Oxygen, 16 grams per mole. Again, looking at the periodic table, you can get the AMU. That means H2O is 2 hydrogens, which is 2 grams per mole, and 1 oxygen at 16 grams per mole. So that's a total of 18 grams per mole. So 18 grams equals 1 mole of water. So that was just a run through on finding the number of moles or finding the number of particles that you have in your sample. So how many gas molecules can we find in an individual container? Let's get back to gas laws. An ideal gas occupies a volume of 100 cubic centimeters at 20 degrees Celsius and has a pressure of 100 pascals. How many gas molecules are in this container? Well, think back. Even though I stopped and did quite an aside on moles and grams per mole, let's think about this now in terms of the ideal gas law. PV equals nRT. How many gas molecules are in a container? We've got a volume, we have a temperature, and we have a pressure. Now, when it talks about the number of molecules, some people decide to go to the combined gas law. That won't tell you N, and that's what this is asking, N. So PV equals nRT anytime you are talking about the number of molecules. That can be rearranged, so N now is PV over RT. Substitute our values in. Now, if we look at our values, here we have P, the 100 pascals. This, so it will go in with the pascals. This constant R here, of course, of 8.31, and our 293 here in terms of T. This is a converted to Kelvin 20 Celsius here, and this, as I said, is now the volume converted to meters. So this is in meters. 1 times 10 to the minus 4 meters, cubic meters. So this will equal 4.11 times 10 to the minus 6 moles. So you may have been wondering why I spent so much time on that aside talking about Avogadro's number and little n. And here is the reason. Our ideal gas law was pressure times volume equals nRT, where this was the ideal gas constant. Now, there is a slightly different version of the ideal gas law that I call ideal gas law version 2. And that deals with the total number of molecules in your sample. So in other words, not the number of moles, but how much gas have you got? And the total number of molecules in the sample, big N, is equal to how many moles of the material you've got times Avogadro's number. So the ideal gas law can be written in terms of big N, the total number of gas molecules that you have. In other words, PV equals nRT is equal to N over Avogadro's number times RT, which gives you a new constant K, the Boltzmann constant. So PV is equal to NKT, where this K is 1.38 times 10 to the minus 23 joules per Kelvin. So you've now got two constants to deal with. One of them is your R constant, which is the ideal gas constant. The other is a constant, which is K. So you need to now be careful. Look for little n or big N. If you're being asked to find the total number of particles, then you can use PV equals big N KT. You could, of course, if you have the molar concentration, do little n and then convert it, but there's no point when you have this version to use. So be careful as to which version of the gas law you use. Use K with big N and use R with little n. Do not mix them up. So let's take a look at a problem with this, our last problem of this set. So if we have a 0.1 cubic meter room held at 32 Celsius with a pressure of 101 kilopascals, estimate the number of gas molecules in the room at these conditions. So PV is equal to NKT. That means N, if we rearrange it, is PV over KT. Substitute in P, this is our number of pascals at atmospheric pressure, 101 kilopascals, so 101 times 10 to the 3 pascals, 0.1 cubic meters over 1.38, this is our K, times 10 to the negative 23 joules per Kelvin, times our temperature in Kelvin, which is 32 Celsius converted to Kelvin. Intermediate point, this is the values. This will give us 2.5 times 10 to the 24 molecules. Now remember, this is the number of molecules in a 0.1 cubic meter container. That's quite a large volume, so you should expect to see very big numbers for this result. And that is the end of our discussion on gas laws. We'll continue to talk about heat and thermodynamics next time.